Hi, welcome back. Hope everybody's summer is going well. Today is going to be the second segment on one-dimensional kinematics, and this one's going to involve acceleration. So we need to first decide what acceleration is. Acceleration is the rate at which the velocity of an object changes with respect to time. It can involve speed changes, it can involve directional changes, or it can involve both of those. The unit is the meter per second squared. That is the SI unit that we will use in our problems. However, it really can be any length unit over any time unit squared. So feet per second squared is also a correct acceleration unit. It's just not an SI unit. So very important here, and we'll talk about why this is later, but please do not assume that negative acceleration is synonymous with slowing down. It can indicate that an object is slowing down, but it does not necessarily indicate that. And by the same token, that a positive acceleration does not necessarily mean that an object is speeding up. It can mean that an object is speeding up, but it does not have to mean that. Any speed change will depend not only on the sign of the acceleration vector, but also on the sign of the initial velocity vector. It's very, very important. We talked about average velocity versus instantaneous velocity. We can talk about the same concepts with acceleration. When we represent these graphically, we can see that in this case, for example, we've got an object, in this case it's a rocket, and its velocity, it says speed, but it's really velocity is being plotted versus time in this graph. If you look at the green curve, that is showing us that the velocity is changing as time goes on. In this case, it's increasing as time goes on. The increase is not constant. So the rate at which the velocity is changing is also changing. We don't have a constant change of velocity. That means we don't have a constant acceleration. So how can we talk about average acceleration in this case? Well, we could take 2 points in time. We could say, all right, what is the average acceleration across that time interval? So the interval that they've chosen in this particular example is from time A to time B, which happen to be 8 seconds and 16 seconds respectively. So what they've done is they've noted that at time A, at 8 seconds, the rocket's velocity is 0. At 16 seconds, the rocket is now moving at 800 meters per second in the positive direction. I know it's the positive direction because I don't know if you can see it, but they've got a negative 200 here, which means that really this is my line here. So if I look at this, I know that acceleration is the rate of change of velocity. It's how quickly the velocity changes. So it's delta V over delta T. That is also the slope of a velocity time graph. And if we look at this graph, since it's curvy, we could take, well, the average acceleration between these 2 points would be equivalent to the slope of a line that connects those 2 points on this graph. So that little thin black line is just connecting those 2 points. We could have done the same thing with a position time graph when we're talking about velocity, when we talked about average velocity. So the slope would be rise over run. In this case, they've calculated it to be 97.5 meters per second squared. Here, they show on this red line what a constant acceleration would look like. It would have a constant slope with our velocity time graph. So this is indicating that, yes, the velocity is increasing, but it's increasing at a steady, constant rate. Right? In both of these cases, the acceleration is positive. This is a positive slope. Once you get past this flat part here, we're all in positive territory for our slope. And also important to note in this graph is that other than this little flat section where the velocity is actually at 0, we can see it on the graph here, other than that, the velocity is all positive. So the velocities are in the positive part of our graph in both cases, both of these lines. So we have a positive velocity and we have a positive slope, positive acceleration. And we can see that what's happening here, the rocket is speeding up. So that's an important thing to note. And so we have average acceleration across time interval, and that's our definition here. And just as a quick reminder, whenever you see delta, remember, for delta V, that would be V minus V initial. V being velocity, right? So V final minus V initial. All right, now this would be, we're looking at the same graph, but now we're talking about instantaneous acceleration. Remember, instantaneous meant at a particular point in time, which is kind of a strange thing to think about, because really when we do our calculations, for the most part, we're talking about time intervals. But sometimes you want to know, well, what's going on right at that instant? For our purposes in the B course, we don't really have a math tool just yet to really get into that point right there. It would actually be a limit, and we talked about this when we defined instantaneous velocity. So for instantaneous acceleration, really it's defined as the limit as delta t approaches 0 of delta v over delta t. It looks a lot like the other equation. It's the same relationship that we saw as the other equation. But we said that that limit idea meant that we're shrinking a time interval down, so that time interval approaches 0. So that delta, that change in time, that delta, the interval is shrinking down, shrinking down. So again, that's something that you'll learn in calculus, but if we, and probably in pre-calc at the end of the year. But if we look at this graph, if we could imagine shrinking down a time interval so that we can talk about this point right here, this point in time, well, we'd have to be talking about a line tangent to that point to decide what would be the slope of a line tangent to that point at that time. So you literally draw a line tangent, and you go ahead and calculate the rise over the run, and that gives you the slope of the tangent line, which is your instantaneous acceleration. You can also get a computer to draw that for you and get probably a much more accurate representation. But for the conceptual part of it, you can kind of eyeball it and say, okay, there would be my tangent line. It's roughly like that, and I could go ahead and take any 2 points on that tangent line and find the slope between those 2 points, and that would be my instantaneous acceleration. So you can see the difference between those two. Let me flip back and forth. So that's the instantaneous acceleration there for point C. This is the average acceleration between points A and B. So you can kind of see that. Okay. So imagine if you could, imagine taking points A and B and getting them closer and closer together. So in other words, shrinking this time interval down from an 8-second time interval to no time interval, so that you're at an actual point on this curve. Okay, so that's what's happening there. So you're going from this line here to, if we were looking between A and B, it would be somewhere down here, but to a single point, and a line that would be tangent just to that point on the curve. All right. Okay. So we're going to do a few graphical representations, how we can find acceleration or talk about acceleration from a graph. All right, so we'll start out with some position time graphs. We're kind of familiar with those, where we plot position versus time. Let's say just for this set of examples, this is not necessarily, it's not the case for every problem, but let's just assume for this set of examples that the positive x is going to be let's just say it's to the right or rightward, and then negative x is going to be leftward. It could be anything. It could be east and west, north and south, in and out, or as we have right and left here. So if an object was sitting still, we did this before, it was sitting still, I don't know, 5 meters from our origin for a period of time, the graph might look like this. If I could draw a straight line, our graph would look like this, and that's pretty simple. The object's not moving. Time goes on, its position hasn't changed. Well, if it's not changing position, then there's no velocity, and in that case there's also no acceleration. So both our acceleration and our velocity vectors are 0. All right. If an object, let's say it starts at whatever our arbitrary origin is, and it moves to the right for a little while, like this. Okay? During this time interval, whatever that time interval is, we have a constant positive slope on our position time graph, so we have if we were to take the slope, find the slope, it would be delta x over delta t. So we have a constant velocity, and it happens to be positive. We've got a positively tilted slope there, right? Positive slope, positive velocity. All right, is there an acceleration here? Not during that time interval, because constant velocity means acceleration is 0. All right, now let's suppose that after that first time segment, we have the object sit still again, and then maybe we have a slope like this. So now here we've got a negative slope. So this again, position time graph means negative velocity. Do we have an acceleration during this time interval? Not during the time interval. So again, A is 0. Now, some of you might be thinking, well, it changed velocity. It was sitting still and now it's moving. Yeah, there was an acceleration, but it was right in here, right at that point. And we can't really zoom in on that point with what we have available right now. But yeah, there had to be an acceleration right in there for a very small time interval. I tried to make that kind of a hard turn there. But we know that the object was moving rightward. It stopped for a bit, and now it's moving leftward. But through the time intervals themselves, we have constant slopes on our xt graphs, so we have constant velocities. And then up here we have a 0 velocity. So in this entire graph, except for these locations here and here, which we don't have enough information about to calculate right here. I mean, we could do it, but we're not going to do it right this minute. Right here and right here, we do experience accelerations, but the time is in between. We have constant slopes. Okay, so we could say that for those times the acceleration is 0. What if we see a graph that looks like this? And it curves. Well, in that case, we're starting at our 0 location, our origin, moving to the right. So we're moving rightward, but are we moving rightward at a constant rate? Is our slope constant? It's not. It's changing. So just by definition of acceleration, if we've got, remember, acceleration is a change in velocity over time. This and the slope of an xt graph is velocity. So we have a changing slope for our xt graph there. We have a changing velocity over time. So we have an acceleration here. So we know that we have positive velocity throughout. It's changing, and it's changing in a positive way. In other words, this object is, its velocity is positive the whole time, and it's growing. It's getting farther and farther away from 0 in the negative part of the world here. It's getting more and more, it's gaining speed, it's going in the positive direction, so we must have a positive acceleration here. The rate is increasing to the right, okay? On the other hand, if we see something like, I don't know, something like this, what would that tell us? Well, we started out with a pretty steep slope here, and it's kind of getting more gentle and then even more gentle, almost to no slope over here. Again, this is x, this is t. So what's happening? We're moving pretty quickly. Well, that's kind of relative to what the scale is. We don't really know, but we're moving faster here than here, which is faster than here, and so forth and so on. The slope is getting shallower and shallower as we go on through time. So we know the velocity is changing. The velocity is negative. We're moving from a position that's far to the right, closer and closer to the origin. So the object's moving leftward. So by the way that we designated here, we have negative velocity throughout. That negative velocity, however, is getting smaller and smaller because the slope is getting smaller and smaller. So that means we have an acceleration. What's the sign of that acceleration, though? This is tricky. If we have a negative velocity initially, but we're slowing down, so we have a negative velocity initially, we're slowing down, we can see that the rate at which that displacement is occurring is getting smaller and smaller. The slope is getting smaller and smaller. If that's the case, and it was a negative velocity, a leftward velocity, we must have had a rightward acceleration to slow it down. So this is a positive acceleration.